Subject of today is the stabilization of carbocations. We start from alkyl halides, tertiary butyl bromide, and here we have allylic bromide. We put it into a polar solvent that could, for instance, be DMSO. This is the structure of DMSO, highly polar with a strong delta minus at the oxygen and corresponding delta plus at both CH3 groups. In a polar solvent, this compound can form those separated ions. What kind of stabilization do we have here? First of all, the bond angles become larger from 109 to 120 degrees from an sp3 hybridization to an sp2 hybridization. Thus, the methyl groups can adapt a position further away from each other. That means here we have a release of steric strain, stabilizing this molecule. Then we have an inductive stabilization of that cationic charge. The cationic charge is a little bit distributed over this molecule. Inductively, electron density is pushed a bit from the hydrogens over that carbon in the direction of the center. Therefore, we will also get slight delta plus at those hydrogens at the periphery. Then, in addition, of course, a stabilization by the solvent. These ions are solvated. That means around the bromide there will be the solvent molecules, preferentially with the delta plus part in close proximity to the bromide. And here, close to the cationic charge in the center, there will be oriented the free electron pairs of the DMSO oxygen. So, one oxygen might be in close proximity here, and on the other hand, on the other side, another molecule will be here. Yeah? So that this will remain planar. Let's have a look at the allylic bromide. In this case, it will give allylic cations with the bromide counter an ion. Here we have a mesomeric stabilization. That means two mesomeric structures. The truth is in between. We can draw it like this, because indeed the bond length of this side is the same as of this side. We have a bond order of 1.5 on each side and not 2 on one side, 1 on the other side as the bond order and somehow flipping. No, this means the truth is in between. It makes sense to draw an energy reaction scheme. Then we have to decide, is this structure or that the energetically favored one? Well, let's start here. Put a starting point somewhere, and will this be above or beyond? Well, clearly it will be above. Maybe here, because this is a reactive intermediate. We have to put in energy to let this form ions, and this usually runs over a transition state. And here, this is transition state, this is reactive intermediate. So, this can also react the other way around to the starting material, and it is clear that also from this drawing it can faster move from the reactive intermediate to the starting material than the other way around. And that means we should put another arrow in this direction. Since the reaction from here to there is faster than from here to there, we will have some concentration of that, but a rather small concentration of that in there. In this case, this is more stabilized than this one, because we have in addition the mesomeric stabilization, and this usually works far better than inductive stabilization. So that means, okay, this is more stabilized than that. It reacts not as fast in this direction as here, but also here is the starting material, of course, preferred. Thanks for listening.